So hello everyone. I'm actually very happy to be here. I'm Argentinian and I have never been further away from my house. So thank you for the opportunity and thank you for having me. So my talk, it's about a project that started as and still is really, a way to encode quantum information in an autonomously error-protected way in an oscillator. So it's going to be a cat qubit. But as we developed these ideas, we realized that the system is much richer than the two-level subsystem that encodes the qubit. It's a full Hamiltonian, and it has very rich physics. So in the context of this conference, I think I'm going to just talk to you about the Hamiltonian, and you'll see that this is a driven system. The talk is about the control of tunneling in this driven system and the thermalization in this out of equilibrium Hamiltonian. So the main thread of the talk is this Hamiltonian that I'm showing you here, which is a very elementary quantum optical Hamiltonian. It's Kerr plus Cuisine, and it almost doesn't get any simpler. This model is very old. It had a lot of attention during many decades, really early on in quantum mechanics. I need to start somewhere this story, and I'll start around the time I was born in 1993, when Billing and Milborn were fascinated by this system because it was a quantum optical model that exhibited ground state tunneling. So tunneling between what and what, you may say. Here you don't really see what's tunneling. But if you make a semi-classical picture of this and you draw phase-space portraits, you see that you have a double well structure. It's pretty easy to see if you remember that the annihilation operator is nothing but the phase-space, complex coordinate, complex notation for the phase-space coordinate, which is x plus ip. And then by unraveling the A and the A daggers in X and P, you see that you have a double well structure. By evaluating P equal to 0, you see you have the typical thing you would expect. And later on, many decades later on, this other Hamiltonian was found interesting, but for the absolute opposite reason. It has absolutely no ground state tunneling. And mathematically, that's very easy to see. I'm going to do the derivation for you in two lines. So you note that this Hamiltonian up here can be decomposed in this factorized way. And if you remember that the annihilation operator A has as eigenstates coherent states, then you see that by taking coherent states of the right amplitude, you will annihilate the Hamiltonian. So now I have plus alpha and minus alpha of the right amplitude that essentially have the same energy, which is 0. And because this Hamiltonian is the multiplication of an operator and its Hermitian conjugate, then you see that energy 0 is the ground state. There can be nothing negative in energy. And these two coherent states here are actually the things that live down in the bottom of these wells, okay? But this is a very special double well in this case because there is no tunneling. It's a fundamental degeneracy. There is no tunnel splitting, okay? Any superposition of these coherent states is going to still have the same energy, and that means it's a good idea to put it in a Bloch sphere. So this is the cat qubit we have been talking about. You see, these are the coherent states, and they're not really orthogonal, but you see that if you take the even and odd superposition of them, that's the even and odd cat, and those are orthogonal. So those go to the north and the south pole of the Bloch sphere. Good? So the interesting thing, though, is that these Hamiltonians, they have both the same classical limit. They only differ from each other by a permutation of non-commuting operators that vanish in the classical limit. And this is very curious because if I give you this classical Hamiltonian, how are you going to quantize it? Are you going to quantize it like this, or are you going to quantize it like that? Because you better tell me. I'm going to make an experiment, and I'm going to tell you which one is the right one. This is a very fundamental problem in the quantization of quantum mechanics. It's understood, but it's actually very important for the rest of the talk. Because you note that the difference in between these two Hamiltonians is the ordering of Kerr, and when you take the difference, you just have a harmonic term. So I can look at a different Hamiltonian that looks like this, that will allow me to interpolate in between this Hamiltonian with quantum tunneling and this other Hamiltonian with absolutely no tunneling. We're not talking about the suppression of tunneling, we're talking about the exact cancellation. And then by taking different values of this parameter delta, I can interpolate in between the Villinger Hamiltonian and the Kerr-Cat Hamiltonian. That's how we call our qubit, the Kerr-Cat qubit. Okay, so I'm going to show you that I actually can control all the parameters in that Hamiltonian in an experiment. This is how the experiment looks when it's open. This is a dilution refrigerator. This is the mezzanine, which is at 10 millikelvin. And inside one of these cans, I have a package that looks like this. This is aluminum. These are SMA connectors. This is copper. And in this pedestal, I have 2 sapphire chips. Think of it of only one of them, because only one of them is going to be involved in this talk. This is a magnification of the sapphire chip. These black things are the superconducting electronics. And the main character of my talk is the transmon qubit that lives there. And it's just two pieces of aluminum printed on the sapphire, connected by a very thin line, which is also made of aluminum, but interrupted by a Josephson junction array. There are two loops, superconducting loops, interrupted themselves by three big Josephson junctions on one side and a small one there. This is called a snail transmon. And if you've never seen how one looks, this is an electron beam microscope picture of the three big junctions on one side at the small junction there. What I'd like you to understand for this talk is that we are going to be driving this system permanently, okay? And this drive is going to generate the parametric squeezing of the Hamiltonian I showed you in the previous slide. Something else I need you to see is that this circuit has currents and voltages, and there is an oscillation, okay? It's an electromagnetic oscillator. And if I measure the voltage, well, I will find it has fluctuations. Those are 0-point fluctuations. They're fundamental quantum fluctuations. And if I measure the voltage, I cannot know the current. So voltage and current, they are canonically conjugated in the same sense that position and momentum of a mechanical oscillator are. So I'm going to call them suggestively P and X, and they will commute like IH bar. And then that gives me handles of the system. For example, there is this X external that I'm showing you there, which is a current I just put through the circuit, okay? And it's a parameter that allows me to modify the circuit. In terms of a mechanical oscillator, this X external will be the equilibrium position of the oscillator, okay? For example, and it's going to be important in a minute. So the Hamiltonian of the circuit I showed you looks like this. It has a kinetic energy term, which is P squared. It has a potential energy term that looks like the cosine of X. This is called the Josephson potential, but it's really like the potential of a pendulum hanging from the roof, where X will be the angle and cosine is the projection of gravity against the vertical. And then the critical thing is that here I have a time-dependent term. T is time, and I'm just driving my circuit via the momentum coordinate. And then the delta parameter I showed you in the previous slide, this is another writing of the same squeeze curve Hamiltonian, is controlled actually by the frequency of the time-dependent drive, which I'm putting at essentially 12 gigahertz for the experimentalists here, which is 2 times the small oscillation frequency of this oscillator. This is the parametric squeezing condition. Now, there is a Kerr nonlinearity here. So this is the nonlinear part of the Hamiltonian. You see you have x to the 4. And this Kerr constant is controlled by the x external I showed you in the previous slide. You can imagine that you have a very nonlinear oscillator. If I move the equilibrium position, then I'm changing the small oscillation nonlinearity, okay? And that's how I control the Kerr constant. Finally, well, I need to say that Kerr is going to be 320 kilohertz in this experiment. At the level of the effective model here, you don't really care because everything is going to be written in terms of K as the units of the problem. But in order to make this rotating wave approximation valid, this thing, it turns out to be very important. So it's not going to show up again. It's going to be in units of Kerr, but it's 320 kilohertz for the experts. And then you have, so essentially I control this with the X external. I think I said that already. And then I have the squeezing amplitude, which I control with the amplitude of my driving force. So this is a Floquet Hamiltonian. The driving is periodic, but I'm telling you that I can do the rotating wave approximation and I actually can forget this has quasi-energies for a while and think of it as an ordinary Hamiltonian without time dependence with energies, okay? And then there is a lot going into this transition. There is some studies that we did there theoretically, but this talk is in the regime where this is valid. So again, here you have the Wigner transform of this Hamiltonian operator. It's a double well surface in phase space. And I'm showing here the Wigner functions of the eigenstates of this Hamiltonian. These two are the coherent states I talked to you already. These are the excited states of the wells. And here you see you have Fock state 1, Fock state 2, almost that. And once the state has enough energy, it's above the barrier and it's just delocalizing between the two wells. And something I also be using heavily for the rest of the talk is that the height of this barrier is controlled by the squeezing amplitude epsilon 2. The height of the barrier is epsilon 2 squared over k, and it's just the amplitude of the driving. Something else that you'll need to know to appreciate the experimental data I'm going to show you in the next slide is that by changing delta and epsilon 2, here already in units of Kerr, I'm able to change the shape of this energy surface. And then you'll see that I can control the tunneling paths in between one well and the other. And there is quite some surprises there. You see, if delta is negative, I have only one well, then I have a double well region, and then I have a double well region with some interesting thing happening in the middle. It's just taking this and plotting it in Python. So again, I'm going to look at this Hamiltonian. Now in the condition of delta equals 0, this is the resonant squeezing condition. And the Hamiltonian looks like this. It's just kerr and squeezing. And if you just take this one and diagonalize it, you can plot the eigenenergies as a function of the parameter epsilon 2. And then you see that you have levels that are in pairs and they exponentially approach each other. This is not one, but the characteristic of a double wall potential. You see, this is how it looks. These two here are very deep in, so they are degenerate. And then you have some state that are here, they are still degenerate. And at some point, there is some tunneling here. You see there is some leaking because the energy barrier is not high enough. So this plot is made around epsilon 2 over k of 7. So you see here you have the two ground states, the two Gaussians. Then the first excited state, they are already degenerate. They are really deep buried into the wells. This one, they're not fully degenerate, so there is a little bit of tunneling there. This is the tunnel splitting of the spectrum. And then the fourth level already, it's completely splitted. It's not even tunneling, it's above the barrier. So how am I going to measure this? Well, this is the experimental sequence. The x-axis is time. And what I'm doing is I'm going to ramp up squeezing. So now I have a double well. Otherwise, I would have just a kerr oscillator. And then I'm going to make a measurement. This measurement I do by homodyning. So I can learn which coherent state I have. And I can do this with very high quantum non-demolition fidelity, 99%. So by measuring, I prepare. So this is a von-Neumann projection that prepares me in one of these two states depending on the outcome, say the left one. Then I'm going to apply a spectroscopic pulse that has as an objective to connect the ground state to one of the excited states. If I hit a resonance, then I'm going to transfer population from down here to up here, where it's actually able to tunnel. So if I wait for a little bit, it's going to fall down to the ground state again. And if I actually was able to transfer population, it may fall on the other side. So by asking a measurement again, did you stay in the same well I find you at the beginning, then I'll know if I actually hit it a resonance with this spectroscopic pulse. I do the experiment. Here is the epsilon 2 axis, the squeezing amplitude. Here is the energy of the spectroscopic tone. In color, I have the probability of transition in between one coherent state to the other. Yellow is the background, meaning I'm hitting nothing. And the color here is that I actually hit one of these quasi-energy state resonances. I take this theory here and put it on top of the graph. It just looks like this. This is remarkable disagreement. This is not a fit. This is an independently calibrated theory plot that tells me that I really understand what's happening. And something else I can do is essentially not make a spectroscopic tone, prepare by measurements, and then wait a variable amount of time to see the thermal activation that will essentially make the thermalization in this parametric oscillator. I start with a coherent state. If I wait long enough, I'm going to end up in a mixed superposition of the two wells, and this has a time scale that I'm calling here T coherent. And what you see is that it grows up, but in steps. And these steps are the incoherent manifestation of this Hamiltonian structure. I have a step every time I have a pair degeneracy here, which means that as the levels go deep and deep in the wells, they sink and they tunnel degenerate. And at some point, the tunneling is negligible and I have a big jump. And I'm limited by the next state that for a while does nothing because it's not inside the well, and at some point it falls in the well and degenerates exponentially, tunneling. And then I actually find that this reflects very well the spectrum. And please note that I'm not talking about any decoherence model for this. Okay, it's a completely Hamiltonian argument that reflects the incoherent properties of the system. Okay, and there is a very nice semi-classical argument that allows you to know when these steps are going to happen, essentially when you're going to have these degeneracies, and for that you essentially need to quantize the classical orbits here and essentially ask that they enclose one quantum of angular momentum. And then that gives you that in this axis, the steps are going to happen at pi, 2 pi, 3 pi. And that's quite nice because it's Bohr quantization in an out of equilibrium system manifesting itself in incoherent properties. It also, you can see it here also in the degeneracies. They happen at pi, 2 pi, and 3 pi there. So now I'd like to tell you about what happens if I turn on delta, okay? The first thing you would notice is that this factorization condition is not true anymore. The coherent states are not eigenstates states of the Hamiltonian anymore. Essentially what happens is that turning on delta deforms the potential. At the beginning, you had two minima and a maxima. But now you have two minima, a maxima, and two saddle points that were not there before when delta was 0. That, among other things, makes that the shape of the orbits stops being circular down at the bottom of the well, and they take this banana shape. So these black lines here, they are the semi-classical orbits. And then what you also see is that they approach very much here and here, the saddle points. And that means that the system can tunnel from one of the states to the other via two different paths, okay? The experiment I'm going to do is very similar to the one I made before, but it's not going to be spectroscopy, it's going to be dynamics. I'm going to look at the dynamics of this system. What I'm going to do is I'm going to ramp up squeezing, make a measurement to prepare either the left well or the right well, and then ramp the amplitude of the squeezing down so the system can actually tunnel, okay? So the tunnel is sufficiently large to observe it. And then I'm going to wait for a variable amount of time and measure again to see if the system has tunneled from one well to the other. This is the raw data. In the x-axis, I have the detuning. In the y-axis, I have time. And in these 4 frames, what I'm doing is I'm increasing the squeezing amplitude. So essentially, I'm making my wells deeper and deeper. The first thing you see is that these oscillations, which are actually tunnel-driven Rabi oscillations from left to right, decrease in frequency as I increase epsilon 2. Well, that's what you would expect for tunneling. There are dipole wells, the tunnel splitting gets smaller, so the time scale of the oscillation is longer. But the truly curious thing here is that at 0, 2, 4, 6, and 8, when delta over curve, it's an even number, the tunnel period diverges. There's no oscillation, okay? And I'm going to analyze this data for you, and to do that, I'm going to fit a damped cosine on it. From the damping, I'm going to get a time scale for the, the coherence, and from the frequency of the oscillations, I'm actually going to get the tunnel splitting. I'm going to get the frequency at which the thing is tunneling. I'll do that like this. Here in pink, I have the time scale, the decay time of these oscillations, but let's ignore it for now. The important thing, or what I want you to focus at, is this plot here, which is the energy difference, the frequency of these oscillations. And what you see is that, indeed, at 0, 2, 4, and 6, the tunnel splitting gets to be exactly 0, okay? So these two levels, they are completely degenerate. And the physics behind this is surprising. There is a paper, a theory paper from 2007, that is called Interference in the Classically Forbidden Region. And what they do is they take essentially this Hamiltonian, thinking of a nanomechanical oscillator really, but our experiment is in superconducting circuits, and this is related to the fact that momentum and position of an oscillator are really analog to currents and voltages, so we actually can make the same experiment. And then what you have in black is the diagonalization of the Hamiltonian, exact, which we also have here on top of the data, the black lines, and it just agrees perfectly. But in the theory paper, they actually make a WKB semi-classical calculation to get the red dashed line there. And you see that you capture very well these degeneracies. And what happens is that in these two tunneling paths that you have here, actually you have interference. The two paths can interfere from one well to the other and destroy each other. And if they do that, then the tunnel splitting goes to 0. And this happens periodically. This is very curious in the following sense. If you are in the classically forbidden region, that means that you have more potential energy than total energy, right? That means that your kinetic energy is negative. If your kinetic energy is quadratic in the momentum, then it means that your momentum is purely complex. That is the ordinary exponential decay you would see in your first course on quantum mechanics. We are not in that situation. Our kinetic energy is actually p to the 4. It comes from the Kerr term here. And if you have a p to the 4 term which is negative, the roots are 4, 2 complex and 2 real. That means that I have 2 real tunneling amplitudes that are going to actually pick up a phase when I go from one well to the other. That is the special interference effect that we're exploiting here. And it's a relativistic-like effect because p to the 4th is the type of kinetic energy you would get if you would expand Einstein's square root, right? This is the Kerr-Cut original working point, delta equals 0, and you see that it's only one point of many. So why would you choose that one? And this is where the punchline of my talk comes. Well, here I'm also showing different shades of green, the amplitude of these different hills, which as I increase epsilon 2, they decrease, you see, from violet to the lighter pink. And they actually behave exponentially. So here I have in shades of green the different amplitudes of the tunneling, and indeed, it goes down exponentially as a function of the barrier height. This is exactly what you would expect for ordinary tunneling, but this coherent destruction of tunneling, it's the particular thing. And if you are familiar with Peter Hange theory for coherent destruction of tunneling, this is very different situation. For the experts, there is a double well potential which is modulated, and you get a similar effect. But here, that's not the case. We have a pendulum which we are driving into parametric bifurcation, and then we make coherent destruction of tunneling of the Floquet states, of the bifurcated states. The driving here is very, very fast in comparison. So it's really a different parameter regime. Finally, I want you to think, or I want to share with you that this effect is also true for the excited states. And to show you that, I'll ask you to forget about squeezing for a minute. Now this Hamiltonian is completely diagonalizable. It's diagonal in the Fock basis. And then it looks like this. Essentially, the eigenenergies of this Hamiltonian, they are essentially n times n squared. And as a function of delta, they are lines with slope n. And I can plot that for you. These are the lines of the different energies of the Fock states as a function of delta. And because I'm going to do spectroscopy, I need to refer this to the ground state, okay? So let me plot this thing with reference to the ground state. The same spectroscopy I did before, I'm going to do now as a function of delta. Well, this is how the spectrum should look like. But now I'm going to turn on epsilon 2. And you should very clearly see that epsilon 2 preserves parity. Essentially creates photons in twos and removes photons in twos. So if I have an even odd crossing, it will remain an anti-crossing. It will remain a crossing, sorry. And if I have an even crossing, they will become an anti-crossing. And I'm going to show you a little animation. As I put epsilon 2 larger and larger, what I see is that indeed some things remain crossings and some things anti-cross like that. And I keep going, if I can. And then this is the way it looks. And then if you look at here down below, then you see that that already show you that data. These oscillations are exactly the oscillations we saw before. But now I want you to see that these crossings, they also happen for the excited states, okay? And actually, they're completely independent of the amplitude of the squeezing. In fact, the formula for these degeneracies is delta equal 2m curve. So every time I have an even number here, I'm going to have degeneracies everywhere there. In fact, if m is an integer number and delta is equal to 2m curve, an even multiple, then I have m plus 1 exact degeneracies in the spectrum. So here I have 1, here I have 2, here I have 3, here I have 4. And they are completely independent of epsilon 2. So now I'm going to increase epsilon 2, and you see they're still locked. The one in 6 is in 6. And that means that I'm not only destroying the tunneling of the ground state, I'm also destroying the tunneling of the excited states. And this is going to affect the thermalization of the system, because now I'm going to jump by a thermal excitation, say, and tunneling is forbidden. So I need to fall back in the same state. Well, measurement is going to be exactly as before. I'm going to ramp up squeezing, prepare one of the states, put a spectroscopic probe, see if I hit something, and then ask the system if it changed. And I do that. This is the data. And you see in dashed lines again that this is, again, a theory independent. It's a theory plot without free parameters. That's the right way of saying this. And it matches quite well. So this is very satisfactory. And what I can plot for you now, this is for a given value of epsilon 2, of course. And what I can do for you now is plot the thermalization time in this double well system as a function of delta and as a function of epsilon 2. So the barrier depth increases in this direction. And what you see is that by going deeper and deeper into the wells, you don't really win that much. On the other hand, by moving delta and exploiting this interference, then you see these resonances at 2, 4, 6, and 8. In fact, for delta equals 0, which was the original qubit operation point, you get in this plot up to 300 microseconds, but you can get up to 1.4 milliseconds if you essentially pump less, but go to the right resonance condition. And again, it's because you're blocking the tunneling from the ground state, but now you're blocking the tunneling of the excited state, and then you're blocking the tunneling of the upper excited state at finite barrier height. So this is an interference effect. Thank you. And well, that's my talk. What I'd like to say is that there is this thermalization of the double well system that depends heavily on the excited states. which are Floquet states really, but I didn't need to use that at any point in my talk. And this is going to actually help us, you already did, to increase the coherence time of our qubit by exploiting this kind of funny relativistic-like effect, which is originally a curiosity thing, but it ended up being something that may be useful in the end. And for that, we exploit the interference in the classical forbidden region. And to connect back to the topic of the conference, my little contribution will be the following observation. Look what happens. If I pump really, really strongly, epsilon 2 is an amplitude in my drive, is my Hamiltonian, then what happens is that my fridge actually heats up. It's funny to see. We're operating a single cat qubit and the fridge heats up. Guess what was going to happen if we put 2 or more? And in terms of timescales, which I'm calling in this talk thermalization timescale, but is really one of the bit flip times of the qubit, then I get all the way up to 500 microseconds. But if I actually pump much less, here around 2 times curve for the squeezing amplitude, then I actually can use the interference of tunneling to get lifetimes that go, well, in this case, up to 1 millisecond. So I have a factor of 5 that I reduce in the amplitude, the power is squared, and I actually get a better qubit, so that's a factor of 2. So essentially I'm getting orders of magnitude in the dissipation in my fridge, okay? Because the lines are heavily filtered and all that energy essentially needs to go somewhere. So that's it. Thank you. So this is a picture of the group, and the people that should be credited for this work are Michelle, Nick, and Jaya. So we work very closely together. It was a pleasure. Thank you very much for your attention.
Thanks, Rodrigo. We can have a couple of questions.
Yeah, thanks. Well, maybe I'll shout. It's a beautiful talk. Yeah, but it's impossible to speak, right?
Okay. I think you can try. I'm going to turn off my mic.
No. So yeah, so a beautiful talk. I was wondering if you keep the full cosine, does this property of the tunneling is suppressed at still exactly the same points, even for excited states?
Right. So if you look at the Floquet Hamiltonian, there is no parity preservation at that level. Right? So the parity preservation is an emergent property of the static effective Hamiltonian. However, there are other properties of symmetry that actually enforce this type of simultaneous degeneracies. So we actually wrote a paper, like a theory paper, about the symmetries of the extended effective Hamiltonian. It's still not the full cosine, but it's the very high orders in the rotating wave approximation, higher than you actually may be willing to look at.
So maybe we can have the next speaker set up, and in the meantime, if there's any last question.
So thank you for a very nice talk. I had lots of questions, and each time I had a question, you answered it on the next transparency. So I just have one question that's left. That is, the original Hamiltonian you showed with the P and also with the in terms of momentum and position, you said you got some ambiguity when you quantized it, or that you could have 2 different Hamiltonians that would have the same classical limit. But when I just tried quickly on a bit of paper to do the reverse, to take the thing in P and X and quantize it the way we were taught, I didn't see a way to get both of them. I seemed it took you always to 1. Maybe I made a mistake. So does that mean that actually 1 is the limit of that Hamiltonian and the other one is a limit of something a bit different, or did I make a mistake?
Thank you very much for this talk. We have to discuss later on, but this is really something important to me. My quick message is that quantization does not work. There is a theorem that is called Groenewald's theorem that tells you that you will never find a map that maps the Poisson bracket into the quantum computator if your function is nonlinear. You just can't do it. Quantization doesn't work. Because you cannot recover quantum mechanics from classical physics. You can recover classical physics from quantum mechanics, but not the other way around. And we should discuss this later because it's interesting.
Let's thank Rodrigo again. And